Hello, this tutorial will help you with naming ionic compounds and writing formulas for ionic compounds. We're going to start with some fairly simple compounds with only maybe a few polyatomic ions in the discussion of this tutorial. I plan on having a more in-depth tutorial posted with respect to additional polyatomic ions in compounds with some more challenging problems soon, so keep a look for that. So first of all, if we want to name an ionic compound, I need to identify if I have an ionic compound first. And so I need to see if I have cations and anions in my formula. Now there's a few things that I might look for. If I'm looking for cations, I usually will have metal atoms present in the formula, as well as nonmetals to represent the anions. That's pretty much a dead giveaway that I have an ionic compound. But also realize there are a few exceptions to this. There are some cations that you might run into out there that have only nonmetals present in them. The most common one that we will run into in our course is the ammonium cation, which is NH4 with a +1 charge. So please note that exception. So our cations may be metals or our polyatomic ions, but we're going to mostly focus on the ammonium cation right now in the course. Now for metals that have only one possible charge state, sometimes we'll say they have only one valency state. Those are metals that are only stable with a certain charged cation that they will form. In those cases, we normally will write the name of ionic compounds with just the metal name. And we will know that the charge of the cation of the metal will result from the only stable cation that forms when that metal ends up being ionized by losing one or more electrons. So some examples of metals that would do this would be the alkali metals. That was our group 1A on the periodic table, that very first column on the periodic table. Those alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, all form +1 cations. Now if we look at group 2, the alkaline earth metals, they also follow this type of trend of having only one possible charge state, also known as one valency. So my beryllium, magnesium, calcium, strontium, barium, we would expect all of those would form just a +2 charged cation. So in all those cases, if I'm writing the name of their ionic compounds, I would write the name of the cation first. And for these, that's just the name of the metal. I will know it's an ionic compound because we'll follow it up with the name of an anion. So to be paired up, they must be ions. I do not use any Roman numerals for these compounds because Roman numerals would indicate that you think that metal cation can have various different valencies, various different charge states. So be very careful about that. Now after I name the cation, I would name the anion. Now there's a few other metal cations that will have only one possible charge state I would like you to remember. There's a little diagonal on the periodic table starting at silver. So silver's a +1. If I go up and to the right, I hit zinc. It's always a +2 that is stable. If I go up and to the right again, it's always a +3 charge state that I predict to be stable on the periodic table. So I would not use Roman numerals on those compounds either. I would just name those compounds with the cation name aluminum, zinc, or silver, followed by the anion name. Now, there's also below zinc cadmium. Cadmium we would predict to form only +2 charge state cations as well. So all of these groups I have listed, as well as individual metals I have listed, we expect to only have one possible charge state. I would not use Roman numerals when I write the name for these compounds. So that's how we would name, first of all, the cations. And just for reference, here's my periodic table showing the cations that we have just listed in green that have only one possible charge state. So if I wanted to name NaCl down here, right below the periodic table, if I look at NaCl, well, I see the symbol for sodium first, so I would write the cation name first, sodium. I do not indicate the charge because we know sodium will only form a +1 charge, so there's no reason to show an indication. And by showing Roman numerals, you would indicate you think it could form other stable charge states, which would not be predicted. Now for the second element here, we see chloride. So we see chlorine, actually, but we know that monoatomic ions would form an IDE ending, usually, so we would see chloride. So you notice the ending of our anion has changed, but the cation name is the same as the original metal name. So here were our monoatomic cations that have only one possible charge state circled in yellow there. Now, if I want to look at the monoatomic anions that I should learn, first of all, they're going to have an ending that goes to "ide." So I'll take the element name, change the ending to an "ide." So for example, nitrogen, when it forms a monoatomic ion, by monoatomic I mean there's this individual single atom that has now gained electrons to become an anion. I changed the nitrogen name to nitride. I want to look at the group number at the top. Now I may see a Roman numeral 5 or a numerical 5A, or I may see a 15 for the column number there, depending on whether I have one version of a periodic table versus another. I believe your textbook should have both at the top of this column. Now, if I want to calculate the charge on nitride, what I do is I look over at the noble gases. Now, the noble gases are the last column to the right on the periodic table. That would be group 18. 18. So if I take the group number 18 and subtract 15, or if I take 15, I misspoke. If I take 15, which was the nitrogen group's number, and subtract the noble gas number of 18, that difference would be a -3. That predicts how many electrons nitrogen would need to gain to have the same number of electrons as the nearest noble gas that follows it. So nitrogen would need to gain 1, 2, 3 electrons to have the 10 electrons that the nearby neon has. That provides extra stability. So that's the charge of this monoatomic anion with the IDE ending. Now, if we look at a phosphide under nitride, again, it's in the same group. We expect it to have in that column the same chemistry as nitrogen, so we might predict it would form the same charged anion, and we'd be completely correct. It gains 3 anions to become the phosphide anion, and that's how we would predict the charge on it. Now, if we look over at the oxygen group, group 6A or column 16, in this case, we can do the same thing we just did with our noble gas group number of 18. If I subtract it from 16, I would get a difference of -2, meaning I need to gain 2 electrons with respect to the oxygen to form my oxide. So in order to gain those 2 electrons, we end up with a -2 charge to indicate the extra electrons that the oxygen atom would have as it forms the anion. Now, with that group, we might expect to have the same type of chemistry. You'd be absolutely right. So we expect sulfur to gain 2 electrons to form sulfide. To be a stable anion here, we end up with a -2 charge on it. Selenide does the same thing. We end up with a -2 charge on selenide. And so we'll see each of these species have the same -2 charge in that family predicted for those monoatomic-eyed anions. We can see that telluride will also gain 2 electrons to form a -2 charge. So those are my predictions for stable-eyed anions for my chalcogens, the oxygen group. Now, if I look at the halides, well, their group number is 17. So if I take 17 and subtract the noble gases group number of 18, the difference is a -1. So we can imagine then that 1 electron needs to be gained by the halogens to have the same number of electrons as the nearest noble gas. So fluorine would gain 1 electron to have the same number of electrons as neon, and we would change the ending to indicate an anion to an IDE, which indicates there's a single fluorine atom which has gained 1 electron to have 10 electrons total and a -1 charge. Now, if we look at chlorine, it forms chloride by gaining 1 electron as well, so it has a -1 charge. And bromide has a -1 charge as well, and iodide. So we can see all the halogens form stable anions with a -1 charge that are monoatomic with an IDE ending as we change the suffix of the original element name. Now let's look at a couple of exceptions to this. I just told you that usually monoatomic ions are the anions we expect to have an IDE ending or suffix. There are a few exceptions to this that I would like you to learn at this point. Please learn cyanide. So my cyanide is not monoatomic. We know it's not monoatomic because there's carbon and nitrogen present in the formula. It does have a -1 charge. I would ask that you learn its name and formula and charge at this point. Hydroxide breaks our IDE rule. It's not monoatomic. Hydroxide is important when we start naming our bases. So I would like you to learn that it has a formula with 1 oxygen, 1 hydrogen, and a -1 charge. Peroxide is the 3rd IDE anion I would like you to learn at this point. It happens to be a polyatomic ion because it has 2 oxygen atoms and a -2 charge. So those 3 polyatomic anions you should learn at this point. And then I would like you to learn a unique polyatomic cation that I mentioned before, the ammonium cation. Now the ammonium cation has 1 nitrogen, 4 hydrogens, and a +1 charge. It is a polyatomic cation with multiple atoms that have lost one electron to have a positive charge. Now, it's one of the few polyatomic cations I would like you to know right now that will not contain a metal in their formula. So this is one of our exceptions I mentioned earlier. So make sure you know that one. Now, another polyatomic cation I would like you to start thinking at this point is one that can be challenging to remember sometimes, because we're now going to use a Roman numeral which does not match the charge on the ion. So let's see what's happening here. So I'm going to look at the mercury 1 cation. The mercury 1 cation actually has 2 mercury atoms in the formula. So you notice it has a subscript 2. Indicates 2 mercury Hg atoms. And it happens to have lost 1 electron per mercury atom, we can imagine, to have a +2 charge total. So we're going to name it mercury 1. You will learn later this relates to oxidation numbers, which we have not talked about in lecture at this point. So remember, even though it's mercury 1, it's Hg2, 2+. Here are some of the common metals that can have a variety of charges. I'd like you to learn these first. We might add a few more to these as well, but these are a good set to learn at the very beginning. Now, if we can have more than one possible charge state, we can't just name the cation by the metal name anymore. Now we need to indicate the charge state, since a variety of charges, a variety of valency states, are possible. So we would like to go ahead and indicate in Roman numerals the charge of the cation when we write the names with these metals that are often transition metals or metals below the metalloid line that can have a variety of charge states. Now, there is an older system for naming compounds without using Roman numerals when we have a variety of charge states for the cation. This can be a little bit tricky, but you'll still run into it in textbooks that are a little bit older than our own. And so I would like you to learn how to name compounds with this older method in case you ever run across it. For example, you might find in our chemistry stockroom that there are a variety of different compounds that are ionic that may have some of our transition metals, and they can be named with the older fashioned naming system where we change the suffix of the metal to an ic or an us. Now, the way we remember this is we look at the metal we're interested in and decide what its common charge states are. So for example, let's imagine we have copper. Copper has 2 common stable charge states, +1 and +2. If I don't use Roman numerals to indicate that, the older method of naming them would indicate, well, which is the common higher charge state and which is the common lower charge state. The higher charge state that's stable for copper was the +2. So I would change the ending of copper's metal name by changing it to an ic. So I would call it cupric. Okay, so if I have a cupric ionic compound with the anion named second, it would indicate that I have the +2 charge. You might remember the higher common charge state is the one with the shorter ending here for the suffix. So now if we indicate the other common charge state of copper being copper 1, well, that we would have for the lower charge state an ending of us, so we would call that cuprous. So I'd have the cuprous for the cation name, and then I would follow that by the anion name. So for example, let's look at a compound that contains copper and chloride. So here we have copper and chloride there. We might ask ourselves, what's the charge on the copper cation? Well, I can use the anion as a guide to determine from the formula what charge would be on the metal cation. Now I know chloride has a -1 charge each. Look at the subscript 2 here. In the formula, I needed 2 chlorides to balance the charge on the copper cation. So that would indicate I must have a +2 charged copper cation. So there's 2 ways I can name this. I can name this ionic compound by using a Roman numeral with the modern system and call it copper, and in brackets a Roman numeral 2, followed by the name chloride, so copper 2 chloride. That's correct, but you may also read the name written with respect to the charge states. Now the charge states at +2 here, that is the common higher charge state for copper, the +2 rather than the +1, and so we would use the ic ending. So I would call this cupric chloride. Okay. Now, if it was a copper 1 chloride, I'd only have one chloride in the formula, so that's how I would tell it from looking at the formula. It'd just be CuCl, and it would be named cuprous chloride. Let's look at a few examples of that. So I have a table of those common metal cations I would like you to learn first with respect to having a variety of charge states that might be stable. So we were looking at copper, right? So we remember the copper 1 cation, if we use the Roman numeral system, that's called the stock system, would be written as copper, in brackets a Roman numeral 1, a capital I. And then the classical name, this was the lower of the common charge states, so I use the longer ending, the us. So I change the suffix to an us. So I would name this cuprous. So this is the cuprous ion. It's the lower of the common charge states. Now the copper 2 plus is the higher of the common charge states. The modern stock system would label that with Roman numeral 2. The classical system would name this cupric. I would call this the cupric ion. So that's the higher of the two charge states. Let's look at a few other metal cations that can follow the stock system or the classical us or ic system that I would like you to be familiar with. Let's look at iron. Now iron has two common charge states that are stable. If you look back at the periodic table example that I showed you a few slides ago, you might recall that we had a +2 charge state that was stable for iron and a +3 charge state we predict to be stable for iron. So the +2 was the lower of the two charge states. If I use the stock system, it's pretty simple to realize the charge because it's just an iron, the name of the metal, and in Roman numerals following it, we show the valency, the charge state of a 2, a Roman numeral 2. Now if I use the classical system, the lower of the two charge states should have the longer ending. We change the suffix to an us. So this would be the ferrous ion. Now be very careful. Notice that the cuprous ion has a +1. The ferrous ion has a +2, even though they have the same type of ending with the classical system of naming them. And that's because the cuprous lowest charge state that we predict to be stable is +1. The lowest charge state that's stable for the iron is +2. So don't try to match the ending to a specific charge. It's just the lower stable charge state for that metal cation would be the us ending. The higher stable charge state would have an ic. So I bet you can guess already what the iron 3 cation name could be. With the stock system, the modern system, we call that iron 3 with Roman numeral 3 in brackets after the name of iron. Now if I use the classical system, we change the ending of the metal to ferric. Now you notice we're using the older name for iron. We're not just saying ionic, we're calling it ferric. So we're using a more traditional name for the symbol originated from. Now if I look at lead, well, lead's lower common charge state, now this is one of our main group metals, right underneath the metalloids. It's right below silicon and germanium in my column 14. Okay, that's the carbon group. So if I look down below germanium, below tin, down at lead, one of the common charge states is a 2+. So I might write it as lead in brackets and Roman numerals 2, or we might use its older Latin name. So we're looking at the ending changing to an us for the lower of the common charge state. So I would call it plumbus. Okay, so this would be plumbus for it. Now, the other common charge states for lead is +4. So lead 4 with Roman numerals is the common new stock system naming. The older classical system would name this as plumbic. We have the ending with an ic. Now, if we look at mercury, my mercury cations are somewhat unique. We can form a polyatomic cation with mercury. So if I talk about a polyatomic ion with 2 mercury atoms with a +2 charge overall for the polyatomic ion, it's in red here because it's not monoatomic, well, we're going to call that mercury 1 despite the fact the charge is a +2. Imagine a contribution from each of the mercury atoms adding up to that +2 when we refer to it as mercury 1. Now that's the lower of the common charge states, so we call that mercurous. Okay, the longer ending the us for the ending of the name changes. Now if we would like to look at the higher of the common charge states, we're back to a monatomic ion with a +2 charge, but there's only one mercury atom that has lost 2 electrons to form this +2 charge, so this is the one we'd call the mercury 2 cation. This is probably one of the hardest of the transition metal cations for students to learn initially because they have that polyatomic mercury 1. So be very careful to learn this one. That's why I've highlighted it in red on this slide. Now, the higher the two common charge states, that mercury 2, the older-fashioned name, the classical system, would be the mercuric salt. So I'd have name it mercuric, and then the anion name, I would know that must be the +2 charged monoatomic ion. Now, tin. Tin, remember the original name stannous coming from your Greek and Latin. If we look there, the common lower charge state, it happens to be in the same family as lead, right? It's below carbon, below silicon, below germanium. We have tin there, then lead. Well, guess what? It forms the same charge states of cations as lead, so it forms a +2 charge state. Okay, so I could call it tin 2, or I could call it stannous. So for the lower charge state, we have the OUS ending. Now, tin 4, with the higher of the two charge states, I can show Roman numerals with the stock system. With the classical system, we use the ic ending, so it goes to stannic. So a stannic ionic compound would have a cation of tin with a +4 charge. So you might have to practice these. I recommend if you're finding these challenging, learn all the cations for metals that have only one valency state first, then begin working on these systems. And realize if I ever have you write the name for an ionic compound, I am perfectly fine with you writing the stock system down. However, if I were to give you the name of a compound, I potentially could give you one of the classical names and see if you can remember the relationship between ics and us's. So let's practice a couple of these. Let's try looking at a compound of lead. So I read on a bottle in the stockroom that I have plumbous oxide. So I'm trying to remember what would that compound be with the modern stock system. So if I have the ending us, ask yourself, is that the lower common charge state or the higher common charge state? And what are the common charge states for lead again? If you recall, lead has two possible charge states we predict to be stable, right? We expect either a +2 or a +4. Okay, so if I have plumbous, the OUS ending classically indicates the lower charge state. Okay, so this would be the lead 2 oxide. Let's name a few compounds from their formulas. So first of all, I will write the name for these ionic compounds by writing the name of the cation first, followed by the anion, following the rules we have been discussing in this tutorial. So first of all, realize that the cation shown here is the symbol for sodium, so we have the sodium cation, so I would write sodium. Do we need Roman numerals? I hope you were saying to yourself, no, because there's only one common valency, one common charge state for ions of sodium. It's an alkali metal. It's in group 1. It forms a +1 charge, and that is the only stable cation we expect to form. Now, because of that, we can look at chloride, and if we remember, chloride has a -1 charge, and it makes sense that we have a 1-to-1 ratio in the formula. So I would write the cation name, followed by the anion name. The anion is monoatomic, so that is why we're using that IDE ending here. So I just name it sodium chloride. So let's try our next formula. So Ki, the K, capital K here, stands for the potassium cation. If you recall, that's also an alkali metal in the first column in group 1. So it has a +1 charge. Now if we look at the iodide anion nets, that's what we would name there. It's a monatomic ion. We're using an IDE ending. So I name it potassium, the cation name first, followed by iodide, the anion name. The anion being monoatomic here is named with an IDE ending. Now please note, no Roman numerals were used here because there's only one possible predicted stable charge state. So potassium, we only predict to form +1 cation, so no Roman numeral was needed. Now if I look at the next ionic compound formula here, we have magnesium, then sulfur. So I name the cation here. Now magnesium, if I look at my periodic table, is in group 2, column 2, the alkali earth metals. The alkaline earth metals. And so the alkaline earth metals will have +2 charges. They will lose 2 electrons to become stable like the nearest noble gas. So magnesium will have lost 2 to have a +2 charge. Now if I look at sulfur, sulfur is in the oxygen family in column 16 on the periodic table. It is 2 away from argon. If it gains 2 electrons, it could form a -2 charged anion that would be stable. At the same electron configuration as argon, it would have the same number of electrons as argon, which is nearby. It gains that extra stability, just like the original inert noble gas would have. So what we can see happening here then is we get magnesium sulfide. So we change the ending of sulfur to sulfide to indicate that monoatomic ion. Again, no Roman numeral needed because magnesium only has one possible stable charge state, A+2. If I were to show the Roman numeral, it would not be correct because you would be indicating to your instructor that there are multiple stable charge states, and the next thing we would ask you is, well, what's the other one? And you're going to say, oh, it's just +2, so I shouldn't have shown the Roman numeral. Now, if I look at FeS here, well, Fe, that's my atomic symbol for iron. I also have sulfur here, and we know it forms monoatomic anions that are sulfides. With iron, I don't know the charge state from just looking at its location on the periodic table. I might remember that it forms stable charges of +2 or +3, so how in the world do I determine the charge on the iron here? What will help you determine this is looking at the anion. I have one anion present, one sulfide anion present, and I should know from the location of sulfur on the periodic table that it forms a -2 charge. It's 2 away from argon. It would have to gain 2 electrons to get that -2 charge, and it gains extra stability. Because the sulfide is -2, and my ionic compound formulas must be charge balanced when I add up all the ions in that formula that has no charge shown, that is neutral as shown, I must be balancing charge out by having a +2 charge cation. So the iron must be +2. Now if I use the modern stock system, I would name that as iron 2 in Roman numerals and brackets after the name iron, sulfide. So iron 2 sulfide. Now that was the lower of the common charge states for iron, right? There's iron 2, then there's iron 3. If I want to use the classical system to name this, what would you name it? Okay, did you beat me to it? It would be the ferrous sulfide. Remember, it's the us for the lower common charge state. If it was iron 3, it would be ferric sulfide, and I would have to have a different formula here. It would not be 1-to-1 in order to balance it. I'm going to show you some examples similar to that in a few minutes, so just stick with me. Now the next compound we want to look at here has CuCl2. Now here we have copper, right? We have the element symbol for the metal of being copper. It's a transition metal right before zinc, right after nickel, okay, and that's in period 4. Now what we can see for the copper is that it's going to have a variety of possible charge states. It's not one of the metals that we learned only had one possible. You may recall, if you've learned them, that it could be copper +1 or +2. However, you did not necessarily have to have that memorized to find out the charge on copper by looking at this formula. The hint here is to look at the anion. I should know the anion charge here. I know chlorine forms chloride anions, which would have a -1 charge each. And how many chlorides are in this formula? I hope you looked at the subscript 2 following the elemental symbol for chlorine. That 2 indicates that I have 2 of the atoms before it, or in this case 2 of the anions, the chloride anions before it. So I have a -1 each. A -1 plus another -1 is a -2 total. So the cations must balance that charge out. There's only one cation, so it must have a charge of a +2. So if I use the modern stock system, I would call that copper, in Roman numerals 2 chloride. Okay. Now remember, copper 1 was the lower of the common charge states for copper. Copper 2 was the higher of the common charge states for copper. So here, since 2 is the higher charge state that's stable, we would use the ic ending for the classical system of naming. We would call it cupric chloride with the older fashioned naming. Okay, so let's look at another example here. Here we have HGO. If you remember, Hg stands for mercury. That's our elemental symbol for mercury. And then so we have mercury and then oxygen. Now mercury can have a variety of charge states. I showed you we had to be careful because there's a polyatomic ion of mercury, which is Hg subscript 2, 2 plus. That's actually the mercury 1 cation. I don't see two mercuries here, so I can't have the polyatomic ion as written. It must be the monoatomic cation for the mercury. So that would be the mercury 2. So just one mercury atom with a +2 charge. It's lost 2 electrons. And it perfectly would balance in this formula because we expect the oxygen to be outside, which has gained 2 electrons to be like neon, right, for stability. And then that would balance out charge for each one of them, a +2 and a -2 for my ions. So I end up with a mercury 2 outside. Okay. So I have a few more we're going to practice. Let's put a few polyatomic ions in the midst now. So you might want to look at some of my other tutorials if you need some extra practice with polyatomic ions. I'm going to be posting some that will have a variety of mnemonic devices to help you remember those. But we're going to have a couple here. So let's look at this formula. Now my cation's first in the formula as shown. So I have the magnesium cation. I know that the magnesium is a +2 because it's an alkaline earth metal. It's in group 2, column 2 on the periodic table. So I will not use a Roman numeral when I name this. I also know that the anion here, if I look at it, it's a polyatomic ion. There's more than one atom present in the anion. And in fact, this is also called an oxoanion because there's oxygen present. So we have nitrogen and oxygen. We would call this nitrate. And so we would name this magnesium nitrate. If you're still working on memorizing the oxoanions, make sure you learn the ones that end with a suffix of -ate first. And my other tutorials will show you how to generate many of the other oxoanion names very easily once you practice them a little bit. Okay, so right now that's a pretty common polyatomic ion, so I thought we might take a look at it. Let's look at a similar example. Let's look at a compound that could be classified as ionic, or really you're going to see we could also classify it as a base. I can classify it as a basic compound because I see hydroxide in the formula, OH- for my polyatomic anion. So my first metal here is zinc. Now if I look on the periodic table, I might recall that there's that stair step of stable cations that can form starting at silver. Silver forms a +1 stable charge state, and so we don't use Roman numerals for it. That's the only charge state we predict to be stable. Our zinc forms a +2, which should be a stable charge state, and then aluminum forms a +3. So here we would have zinc. I would not use Roman numerals because we have learned only one stable charge state is predicted, so I would just call this zinc hydroxide. Name the anion name second. A common mistake is for a student to accidentally add Roman numeral 2 here. Even though that is the correct charge, that would indicate you think zinc should have other possible stable charge states, which is not true. So please leave the Roman numeral off in this case. Now the next compound here, sometimes students will mistakenly classify this as a molecular compound because they'll look at nitrogen, hydrogen, and chlorine and they'll say those are all nonmetals. However, you should recall that NH4 looks familiar. The ammonium cation is NH4 with a +1 charge. And then chloride would have a -1 charge. So this matches perfectly for an ionic compound with the ammonium cation and the chloride anion. So I would name the cation first, the ammonium cation here, followed by the anion chloride. Okay, no Roman numerals needed. Now the next compound we're going to have here, if I look at the metal to begin with, is cobalt. I look at the periodic table and cobalt is a transition metal. It is not one of the transition metals we said were stable, silver, zinc, or cadmium with only a single charge state, so I would tell myself cobalt can have a variety of charge states. If I don't recall the common charge states, how would I determine what they might be? Well, the first thing I might ask myself is, could I use the anion to determine the charge state? This is a polyatomic anion. You may still be learning the formula and charge. But I have carbon and oxygen. It's an oxoanion. I may remember some mnemonic devices that were discussed in other tutorials if you've seen them yet. We would have this named as carbonate. The ATE ending or ITE ending indicates an oxoanion with oxygen present. Look back at nitrate. Okay, nitrate had an ATE ending, so it had nitrogen combined with oxygen. Okay. Here I have carbon combined with oxygen. So I start the name with carbon, ending with an 8 in this situation. So it would be a carbonate. Now carbonate has a -2 charge. So if you notice here, I could have 3 -2 charges. That would add up to a -6 total for the 3 carbonates. When I have multiple polyatomic ions, you'll also notice I'm putting brackets around the polyatomic ion and the number of ions shown as a subscript afterwards. Now, if I have a -6 total for the 3 carbonates, well then all of my metal cations must add up to a +6, so everything adds up to 0 combined. So the cobalt cation must have a +3 charge, and there must be 2 of them here. That's why there's a subscript 2 after cobalt. Since there's a variety of charge states, we need to use Roman numerals, so I could call this the cobalt 3 carbonate. Cobalt 3 carbonate. Now the next compound can be classified as an ionic compound or also as a base. So here we're looking at Fe, that's iron, right? And then we have hydroxide, OH. Now hydroxide polyatomic ions, they were one of the few that break our rules for the IDE ending. So hydroxide, OH, is actually polyatomic even though it ends with an IDE. It's OH with a -1 charge. Now you notice there's brackets around the hydroxide ions and a subscript 3 after those brackets. This indicates that there's 3 hydroxides, a -1 each, so it adds up to a -3 total for all of the anions. So we must have a +3 charge for the iron then. So I have an iron 3 hydroxide. I'd have to show the Roman numeral iron can has more than one possible charge state. If it was iron 2 hydroxide, we'd only see 2 hydroxides in the formula rather than 3. So I can tell the difference easily from the formula. Okay. So let's look at a compound here with mercury. So my metal is mercury. I know mercury can have a variety of charge states. I'm going to have to look at the anion to help determine those charge states. The anion here has phosphorus and oxygen. So I might be saying to myself, this could be an ATE ending on the oxo anion, or it could be an ITE. This is one of the ATE oxo anions with that ending that you should learn first. So it's going to be phosphate. So at the beginning of the name coming from phosphorus, the ending being the 8, so it's phosphate. You'll be learning that it has a -3 charge. Since I have brackets around the phosphate anion and a subscript 2 after them, I must have 2 phosphates. A -3 for the first phosphate ion, a second -3 for the next phosphate ion, that's a -6 total. So my mercury cations must add up to a +6 for all of my charges to add up to 0. So my mercury here would have to be a +2 each. There's 3 mercury 2 cations present in the formula. So this would be mercury 2 phosphate. So keep practicing these with the extra handouts I have posted. Let's try writing some formulas for ionic compounds from their names nets. So we're going to start with the names and try to go back to the formulas. Okay, so this next question I have for you, I'm asking you what the formula is for plumbous oxide. Plumbous oxide. So if we look at the formula here, we have to think, what are the common charge states for lead? I've given you a reference here on the periodic table. It can be +2 or +4. So I need to ask myself, when do I use an OUS ending with the older naming system, and when do I use an IC? So for the US, that would be the lower of the common charge states, whereas IX would be a higher of the common charge states. So plumbous oxide must have lead 2 as part of the formula. Okay, so in this case we would end up seeing my lead 2 cation, and I would have 1 oxide, so the best answer for this one would be A in this one. It would be a +2 lead and oxide with a -2 charge. I'm going to skip ahead. There's actually a typo in the charge here, so ignore that charge right now. We'll look at the next one. Okay, let's look at the crossover rule. So if we look at the crossover rule, what this shows you is sometimes I can look at the charge of my cation and anion and determine the formula by placing a subscript on the oppositely charged ion. Okay, so for example, let's try this with a very simple one. Let's have the name lithium fluoride. Okay, so I'm going to go ahead and find the subscript for lithium from the charge on the fluoride ion, and the subscript for fluoride from the lithium cation from the opposite charged ion. Okay, that's what I'm doing right now. So I look on the periodic table and I realize lithium is an alkaline metal. It must be a +1 charge. So I write down the cation formula and charge to help me get started with writing the formula for the ionic compound. Then I'll follow that by writing the formula for the anion. So I look on the periodic table and I say, oh, that's a halogen. Fluoride's a halogen. It's a -1 charge, so I write the formula for the anion. This is a great way to get started with writing a formula, but the end formula shouldn't show the charges, correct? That's just a way to help reason out what the formula might be. So if I look at this, I look at the fluoride and I think, it's a -1 charge, so I'm going to put a subscript 1 after the cation. And then I look at the lithium cation, it's a +1 charge, so I could put a subscript 1 after the anion, fluoride. Okay, so I've shown that here. Now usually we will not show subscripts 1s. We'll remove them, and if we don't show a 1, it is assumed the subscript is a 1. Okay, so that's where I'm getting my subscripts from, but then I'll simplify that down and just write lithium fluoride as LiF. Without a subscript shown, we are thinking in our heads it means a 1 if there's not a subscript indicated. Okay, so the in the box is the final answer I'd be looking for. If you have the 1s there on our first test or so, I might just mark that out, but I don't think I'd mark a point off yet. But you look like you're just learning the very beginning steps of chemistry if you're writing 1s for your subscripts in this case. We normally would omit them. Now you can also see how the charges for all the cations and anions add up to a neutral compound overall. So we have a +1 for the lithium cation, a -1 for the fluoride ion. We have 1 of each. We add those up to a 0. So there's a double check that I have the right formula when I have the number of each of the ions there. Now let's try another compound. Let's try sodium oxide. Now if you remember, sodium's also an alkaline metal. It's in period 1, group 1 on the periodic table, so it has a +1 charge. So I'd write down the cation formula just to help me get started here. And then I would look on the periodic table for oxygen. I'd see that's, okay, 2 away from the nearest noble gas, so it would form a -2 charge. So I'd write the charge for the oxide ion to help me figure out the formula. Now if I apply the crossover rule, we will see that the subscript for the cation would originate from the charge on the anion. That -2 on oxide would match the subscript for the sodium in the sodium oxide formula. We have a +1 charge on the sodium, so just as a placeholder here, I might write a subscript 1, but we remember that usually 1s are omitted and assumed. So here we would write this as Na2O with the 2 as a subscript after sodium. If we double check charge to check our work, each sodium cation has a +1 charge. So the first sodium cation gives me a +1. There's a second sodium cation with another +1 charge. Then I have the oxide anion with a -2 charge. If I add those up, +1, +1, -2, we add up to 0 for the overall charge on this compound. Okay. Let's practice with potassium nitride. So potassium, again, alkaline metal. It's group 1, +1. Okay, we've done a few of those now, so hopefully you have that down in your memory. Now we need to look on the right-hand side of the periodic table for the nonmetals for nitrogen. Nitrogen is 3 away from my column 18 or 8A, the noble gases, so it would have to gain 3 electrons to have the same number of electrons as the nearest noble gas, so that's going to be my nitride. Okay, so I can look at this. I would write the cation formula down, potassium with a +1 charge. As a placeholder here, I would write the anion name and show its charge just to reason out what the formula would be. So I showed nitride with a -3 charge. I use the crossover rule to try to predict the subscripts in the compound formula. So I say, okay, I have a -3 on the nitrogen, so I should have 3 potassium ions. So I show a subscript 3 after potassium, and where my potassium cation has a +1 charge, I only need 1 of the nitride anions. So I've shown that here with the crossover rule to help remember that. Now I omit the 1. If I don't show a subscript at all, we assume it's 1. So I would actually write K3N. Now I can double check my work by adding up the charges of all the ions in the formula to make sure they're electrically neutral when I add them up to a 0. So I have 3 potassium, so I'm going to have a +1, a +1, and a +1 for each of those 3 potassium cations. So a +3 total for all the cations. And then the nitride would be a -3. So I add that +1, +1, +1, -3. We end up with 0 for the overall charge once we add up all the ions. So I've double checked my work. Okay, I'm a little bit tired of looking at alkaline metals. Why don't we try an alkaline earth metal? Let's look at magnesium chloride right now. So magnesium is one of my alkaline earth metals. I predict it has a +2 charge, being in group 2 on the left-hand side of the periodic table. On the right-hand side of the periodic table, we have a halogen here, chloride, so it should have a -1 charge, monoatomic. So I would write down the formulas for the ions I'm looking at. I write the magnesium cation formula down, followed by the chloride anion formula. I can use a crossover rule to try to predict the number of each of these ions I have. I predict then there would be 1 magnesium cation and 2 chlorides, right? Because my charge on the chloride is -1, so I only need 1 of the cations. My charge on the magnesium cation is at 2, so I need 2 of my anions. So I have magnesium chloride shown. Okay. I leave the 1 and omit it off. Okay, so I have 1 magnesium cation, 2 chlorides. I can double check my work. The cation has a +2 charge. Each of my anions have a -1 charge, so I have a -1 for the first chloride, a -1 for the second chloride. They add up to 0 overall. Okay, that's my magnesium chloride. Now my next compound I will look at is barium phosphide. So if I look at the left-hand side of the periodic table, barium is also an alkaline earth metal with a +2 charge. If I look at the right-hand side of the periodic table where phosphorus is, it's 3 away from argon, the nearest noble gas. So it would gain 3 electrons, 1, 2, 3, and -3 charge. So I write down the cation formula, Ba2+, and then I followed up with the anion formula, P3-. Okay. If I want to use a crossover rule, this can help me determine the actual end formula of the compound. I can end up with barium phosphide, where we can see that the 3 for the subscript for the cation can be reasoned out from the -3 charge on the phosphorus. The +2 charge on the barium can help us reason out the subscript 2 for needing 2 phosphide anions. What really helps us predict this, though, that would be our final answer, but what really helps us predict this is that all of the ions add up to 0. So I end up with a +2 charge for the first barium, a +2 charge for the second barium, and the third barium gives us the third +2, so that's a +6 total. And then I have phosphorus with a -3 for the first phosphide. The second phosphide is a -3, so there's a -6 total. I add those all up to 0. So I double check that everything's electrically neutral. So this will give me the correct answer as long as I have predicted the correct charges on the ions. Now if we look at silver chloride, do we know the charge states for silver? It's not an alkaline metal and it's not an alkaline earth metal. But you recall there were a few other metals that only form 1 predicted charge state that's stable. Silver was one of them. Remember, it starts that little stair step. So silver was a +1 charge. Okay, so that's why no Roman numeral was given here. It's only predicted to have 1 stable charge state. So we're going to go ahead then, and I look at that stair step. That helps remind me of the charges. That will be in my head, though, because it won't be given on a test. You just get a blank periodic table. So it should be a +1 charge. So I write down the cations formula. Then I go ahead and look at the halogens, and chloride should be a -1. All the halogens form a -1 charged anion, I should remember. So I write down the anion formula. So I end up with having a 1-to-1 ratio. If I use the crossover rule, there's a +1 and a -1, so I get a 1-to-1 ratio. We recall that if the subscripts are a 1, we omit them, and it's just assumed if they're not shown, they were a 1 for each of those species. So 1 silver cation and 1 chloride ion for this structure. If I want to double check my work, I can say, well, there's a +1 charge for silver, there's a -1 charge for the chloride, it adds up to 0, so it's electrically neutral for the formula, which is why the formula does not show a charge on it. Now, a common mistake I will see students do is they will write the end formula and leave little charges shown at the top for their notation of their work. Okay, we normally wouldn't show the charge for the final formula because it's electrically neutral overall as a total combined formula. Okay. Now let's look at aluminum sulfide. Now aluminum was part of that stair step as well, right? Aluminum was a +3. That's why you'll notice, even though the group number is sometimes written as a 13, sometimes it's shown as a representative element as 3A, the third column of the representative or main group elements. Okay, so we have aluminum here. We can go ahead and see then that it's +3, so I write down the cation formula and charge. There was no Roman numeral shown because only 1 possible stable charge state was there, so the name didn't give me the Roman numeral here. Now sulfide, if I look over At sulfur, it's 2 away from argon, so it would need to gain 2 electrons to form a stable anion when it forms sulfide. So I'd write down sulfide as S2 minus. Okay, and then I go ahead and write the combined formula of the two. The crossover rule can help me come up with this formula by thinking, I would need 2 of my aluminum cations to balance the charge to get a electrically neutral species when I have multiple sulfurs. So I use the crossover rule here, 2 aluminum cations, and then I use the charge on the aluminum to get my sulfide subscript of 3 sulfides. Let's see why this is true. If all of my ions add up to 0, I should have balanced it correctly if it's the simplest ratio I can come up with. Okay, so I can double check my work. So the first aluminum cation is +3, the second one's a +3, so there's a +6 total. Then if I look at my sulfur, I have a -2 for the first sulfide, the second sulfide is a -2, the third sulfide is a -2, so there's a -6 total from the 3 sulfide ions. So if I add them all up, I will see it adds up to a 0 for the overall charge. Let's consider zinc bromide. So if we look at zinc bromide, I wanted to finish the stair step here. So the zinc was a +2 charge, right? No Roman numeral given because only one stable charge state. So I write down zinc with a +2, and then I look at the halogens for bromide. I realize the halogens form a -1 charge. So they're 1 away from the nearest noble gases, so they gain 1 electron, become stable. So I write the anion name, and we can see here that we have then 1 zinc and 2 bromides using the crossover rule to help me reason out the subscripts. I omit the 1 and write it as zinc Br2. And I look at my charges, +2 for zinc, -1 for the first bromide, -2 for the second bromide, so a -2 total. I end up with an overall combined neutral 0 charge for the entire formula. Now, you must be careful. If students blindly use the crossover rule, there's a few pitfalls and pearls they might run into. Okay? Here's where you need to be careful. Make sure when you come up with the end formula of your compound that you have the simplest ratio of the ions shown. If you can simplify it to a smaller whole number ratio of the ions, you should do so. Make sure you have that simplest ratio of the ions. You must be careful, though, when you simplify that you don't destroy the identity of the polyatomic ion present. Okay? So if you do have a polyatomic ion, make sure simplification doesn't destroy that identity. You should have the same formula for the polyatomic ion when you're done with any simplification. If simplification would change the identity of a polyatomic ion, do not simplify the formula because you would lose information. Okay? So let's look at a couple of examples where we have to be careful about thinking about the crossover rule. Do we have the simplest ratio of cations and anions that would add up to 0 charge overall? So let's look at a simple case where we do not have any polyatomic ions, so just monoatomic ions. Let's consider if we have calcium sulfide. So calcium is an alkaline earth metal. It has a +2 charge, and my sulfide is going to have a -2 charge. So if I use the crossover rule blindly here without thinking about what it really means, I might try to write my answer as having 2 calcium ions and 2 chloride ions, or 2 sulfide ions, I mean. We definitely have the right ratio of ions in order to add up to 0, but it's not the simplest ratio. So this is where the crossover rule can get me in trouble if I'm not thinking about what it means. I really can just have 1 calcium cation and 1 sulfide ion. They'd add up to 0, which is the 1-to-1 ratio. I can simplify those 2's to 1's. So the correct answer here would be CAS, the simplest whole number ratio of the ions whose charges would add up to 0. 1 calcium cation and 1 sulfide. Okay, so be careful. I've been showing you the crossover rule, but here's a case where you have to think a little bit more than just blindly following it. If I check my charges here, that +2 and -2 add up to 0. I just needed 1 of each. I could simplify. I didn't lose the identity of any of the ions by simplifying those subscripts. So to get full credit, I must remember to simplify. Let's look at a case with a polyatomic ion where I have to worry about the crossover rule and having to simplify my answer. So if I have cadmium carbonate, well, cadmium is a monoatomic ion. Cadmium is going to be, I showed the wrong part of the periodic table here. Your cadmium would actually be below zinc. It's one of your transition metals. It was underneath the stair step there, but there was no Roman numeral shown here because only one stable charge state would be present. Okay. Now the carbonate, so I'd write the cadmium cation, ignore column 1 and 2. That's not for this problem. So I have the +2 cadmium ion. I'd write the carbonate ion. The carbonate ion, if you recall, is 1 carbon atom, 3 oxygens with a -2 charge. Now, what might hint to you here to be careful using the crossover rule is that you have a +2 on cadmium and a -2 on carbonate. We have one of each, right? I just need one of each, but if I try to use the crossover rule, you might try to write 2 cadmium cations and 2 carbonate ions. If you try to do that, you might put brackets around the polyatomic ion, which would be the proper procedure if we did have more than one, with a subscript 2 after it. However, if we take a look at this, even though we follow the crossover rule, it's not the simplest ratio. I could just simplify it to a 1-to-1 ratio. 1 cadmium cation, 1 carbonate ion. They'll be neutral when I add up the charges on the ions. I have a +2 on the cadmium, I have a -2 on the carbonate, adds up to 0 overall. So I must have simplified here. The crossover rule, if I followed it and didn't simplify, would have ended up getting me in trouble. So be careful. Don't blindly follow it. Think what it means. We need the simplest ratio of the cations and anions. Okay. Here's an example of an iClicker question I've used in the past. Okay, so let's see if you can choose the correct answer. Let's look at mercury 2 oxide. Mercury 2 oxide. Now, if I want to look at mercury 2 oxide, I should try to write the metal cation formula here, as well as the anion formula here. So I'd start to look at this. I look at mercury, and I'm thinking, Roman numerals must be a couple different charge states. I have to think about whether or not it's the polyatomic mercury ion, or just the +2 charged mercury ion. Remember, mercury 2 is just Hg, 1 mercury atom with a +2 charge. Okay, to pick the right one. The Hg2, 2+, was the mercury 1. That was a little tricky, so be careful there. So then I look over at oxygen. It should be an oxide when it forms. It has a -2 charge, 2 away from neon, the nearest noble gas. So again, if I try to blindly use the crossover rule, I might try to show 2 mercury cations and 2 oxide anions for my subscripts, but I can simplify this and maintain the identity of the ions. I can show just a single mercury 2+ and a single oxide anion, and that's the simplest whole number ratio I can come up with here. So I have a +2 for the mercury cation, a -2 for the oxide, adds up to 0. So the correct answer would be in the box here. The mercury 2 oxide is just shown as 1 mercury cation and 1 oxide anion in the formula. Okay. Now let's switch things around a little bit. Let's look at the mercury 1 oxide. So these are some good examples because you're kind of looking at that challenging mercury 1 cation. Now remember, the mercury 1 cation is actually a polyatomic cation that we must remember. There's 2 mercury atoms and a +2 charge overall for the mercury 1 cation. Okay, so I write down the cation formula. There's a subscript 2 in the cation formula before I even write the ionic compound formula. If I look at oxide again, it's just an O2-. Okay, so if I'm looking at this one here, if you try to use a crossover rule, you might try to write something like this, where you indicate 2 of the polyatomic ions. That's polyatomic, so I need to put brackets around it, right, to indicate that polyatomic ion. And then I can show a +2 for the mercury 1 cation. I could probably try to put a subscript 2 after oxygen. I would hope you might recognize here that I could simplify this ratio to show a simple situation with 1 of the mercury 1 polyatomic ions, right? That 2 is part of the polyatomic ion here for the mercury. Okay, that 2 is part of the polyatomic ions formula. There's only 1 mercury 1 ion there. Okay, and then we have oxide. We just need 1 oxide. So if I look at the charges, a +2 for the mercury 1 ion, and we end up with a -2 for the oxide ion, adds up to 0 overall. Okay. So with this in mind, let's follow along with mercury 1 for a second for another example. Let's look at mercury 1 nitrate. So if I gave this an iClicker question, this might be how I would arrange possible answers. So for mercury 1, we have Hg2, 2+. Remember, it's our polyatomic ion. That one's a little tricky to remember, so practice this one. Now for nitrate, the ATE ending indicates this is a polyatomic ion. In fact, it's an oxoanion when I see ATE as the ending of the name. So I have nitrogen first, 3 oxygens and -1 charge. So I'm going to look at this. If I try to use a crossover rule here, I would indicate just one mercury, one cation, Hg2. So I have a 2 here. That's not part of the crossover rule. I just have one of the polyatomic ions. And then I happen to have 2 nitrates. This makes sense because I'm using the crossover rule to get 2 from the +2 charge on the cation. Okay. Now I might ask myself, what is the correct answer here? What should I write as the final answer? Can we simplify the ratio by taking those 2's and going to 1's? How many of you think we should? If you said we should simplify the ratio, you are not correct for this reason. If I simplify this and write this as HgNO3, that loses the identity of the mercury 1 ion. Ooh, this was a tricky one. This was a tough one, right? So I must maintain the identity of my polyatomic ion so I don't simplify this one because I would lose that identity of the mercury 1 ion as we know it is as a polyatomic. That one was one of the hardest ones you might have with respect to writing ionic compound formulas from the names due to this polyatomic ion. So be very careful. You won't find very many more challenging than this unless you're having trouble with the polyatomic ion formula in general. Okay. Now I can double check my charges. I have a +2 on the mercury 1 cation. I have a -1 for the first nitrate. Those brackets show me that 2 is a subscript outside, so I have 2 nitrates, so there's 2 -1's, adds up to a 0 overall. So for this first tutorial, this is where I'm ending, and I hope you'll find it quite useful. Okay. Keep checking back for more tutorials.